When you see a giant thunderhead building on the horizon, it just looks like nature doing its thing, right? Simple. But the actual science behind how a lightning bolt gets started, well, it's so much weirder and more fascinating than you probably think. So let's dig into what's really going on up there.
We all kind of learned a pretty simple story in school, didn't we? You get some friction up in the cloud, it builds up a bunch of static electricity, and when there's enough of it, bam, a giant spark jumps to the ground. It feels right, it makes sense, and hey, it matches what we see.
Well, here's the twist. For decades, scientists have this massive puzzle on their hands. Because when they actually sent instruments up into these storm clouds to measure the electrical fields, they found something really shocking. The fields just weren't strong enough, not even close to what you'd need to create a spark out of thin air. So, how in the world does lightning even happen?
To get to the real story, we first have to understand how a storm cloud turns itself into a massive battery floating in the sky, and it all begins with a little bit of ice.
The scale here is just mind-boggling. Inside that swirling cloud, you have billions upon billions of tiny collisions happening every second. Little bits of soft hail, which are called graupel, are bumping into delicate ice crystals. And every single one of those collisions is like a tiny negotiation over electrons. One particle comes away a little more positive, the other a little more negative.
And here's the brilliant part. The storm uses its own winds to sort itself out. The lighter ice crystals, which are now positively charged, get swept up to the top of the cloud. This forms a big positive cap. Meanwhile, the heavier, negative graupel sinks down, creating this huge negative reservoir right in the middle. Sometimes you even get another little positive spot near the bottom. This separation creates a gigantic electric field.
Okay, so we have our giant cloud battery. It's all charged up, ready to go. But this, right here, is where we hit that impossible part of the story.
Yeah, like I mentioned, when scientists flew planes and balloons right into these storms, the numbers they got back just didn't add up. The electric fields were only a fraction of what physics says you need to break down the natural insulation of air. A spark just shouldn't be able to form. It's like trying to start a car with a battery that's only at 10% charge. So this is really the heart of the problem. You've got the field strength the storm actually has right here. And then you have the field strength it should need to make a spark way, way over here. There's this massive gap. So the storm is cheating. The question is, how?
Well, it turns out the answer isn't just one thing. It's two conspirators working together in secret to kick the whole process off. And believe it or not, one of them comes from outer space. Okay, so our atmosphere is constantly getting zapped by these super high-energy particles from deep space called cosmic rays. When one of these little bullets hits an air molecule, it can knock an electron loose. Now, normally that electron wouldn't go far, but inside the storm's electric field, it gets accelerated so fast it starts running away, creating a whole avalanche of other high-energy electrons. This is the cosmic nudge that gets the ball rolling. And at the exact same time, you've got our second conspirator. Streamers. Think of these as millions of tiny branching feelers of plasma that sprout off the sharp edges of all those ice crystals. They're like microscopic explorers, carving out little paths and seriously amplifying the electric field right at their tips. They're basically pre-building a weak, electrically charged highway for the lightning to follow. So there's the solution to the puzzle. You've got the runaway electrons from the cosmic rays providing these super energetic seeds, and then you have millions of streamers that take advantage of those seeds and start linking up. Together, they bootstrap the whole process, letting a massive electrical breakdown happen in a field that, by all rights, should have been way too weak. So with that mystery finally solved, we can trace the actual birth of a lightning bolt, from this invisible whisper of energy all the way to that brilliant flash and roar that we see and hear. So get this, the very first sign of lightning isn't light at all. It's a little crackle of radio waves as that initial breakdown begins. From that chaos, a hot conductive channel, we call it a leader, starts to form, and it steps its way down toward the ground. As it gets close, the ground responds, often sending another leader up to meet it. The second they connect, the circuit is complete. That's what triggers the main event, the return stroke. It's that blinding flash of light we see, rocketing back up the channel, heating the air so hot, so fast, that it literally explodes in the shockwave we hear as thunder. Now, not all these leaders are the same. The most common ones are negative leaders. They make those classic, jagged, step-like patterns. But you also have these rarer, much more powerful positive leaders. They tend to move a bit more smoothly, and unfortunately, they're way better at starting fires. And just remember, most lightning, we're talking over 90%, never even leaves the cloud. It's all just happening up there.
Okay, I know this all might seem like some really complex physics, but understanding these secret beginnings, it has huge real-world implications. This isn't just for academics. This stuff saves lives and helps us build a better world. Remember those first little radio whispers we talked about? Well, we've built detection networks that can actually hear those initial breakdown pulses. This gives us a heads up that a lightning strike is forming before the first one even hits the ground, giving airports and people at outdoor events critical minutes to get to safety.
And by understanding exactly how these leaders start and attach to things, engineers can design much safer tall structures, like skyscrapers and especially those giant wind turbines. They can build them to better withstand and safely handle a lightning strike, which prevents all sorts of damage and failure.
Here's a big one you might not think about. Lightning is a huge natural source of chemicals in the atmosphere called nitrogen oxides, or NOx. And those chemicals have a big impact on air quality and ozone. So if you have better models of how lightning starts, you get a more accurate count of NOx, which in turn makes our big climate simulations that much more reliable. And finally, those runaway electron avalanches, they don't just kickstart lightning. They produce very real bursts of X-rays and even gamma rays. For an airplane flying near the top of a thunderstorm, that's a real radiation hazard that we can now actually predict and account for, all because we understand that first little cosmic nudge. So the next time you see a flash of lightning, just remember what you're really looking at. It's not just a single thing that happened. It's the spectacular grand finale of a cosmic conspiracy. Millions of microscopic negotiations and a final, sudden agreement made in midair to complete a circuit. The bolt we see? That's just the signature on a contract that was written in the chaos of the clouds long before our eyes ever had a chance to catch up.